number 9 on the actual homework page. So when you go to turn this in, I only want the back page. The front page is your note sheet. So I want you all keeping that front page because we're going to be doing more graphs on the block. So keeping that front page, that way we know how to graph each form, is something you want to hold on to. Okay, so this is vertex form. And really the only thing I want to go through is finding the x-intercepts here because we're going to get something weird to happen. So when it's in vertex form, and really for any form, when we want to find the x-intercepts, we let y equal 0. Remember, h of x, when it's in this function notation, that represents just our outputs or the y values in general. So I'm going to replace h of x with 0. So I get 0 equals 1/2 times x plus 2 squared plus 3. And so our task is to now get x by itself. And this is where we're going to need to use square roots. So our first objective is to get the x plus 2 squared all by itself. And the first thing that we're going to do to make that happen is we're going to subtract 3 from both sides. So I get negative 3 equals 1/2 times that x plus 2 squared. This 1/2, it does want to distribute, but we cannot distribute into the parentheses because of the squaring. The squaring doesn't allow us to do that. But I know it wants to multiply. If I can't multiply it, I can undo it by dividing. And we can divide by fractions. Okay, at this point, we'll just let the calculator do that work for us. So I'm going to take negative 3 and divide it by 1/2. When you are putting fractions into the calculator, just put them in as division problems. That's all a fraction is. It's really just division. Okay, and that gives me negative 6. So this is negative 6 equals x plus 2 squared. Well, now for us to get the x plus 2 by itself, we need to take the square root of both sides. And so when I go to take the square root on the right side, it does cancel out with the squaring. But when I square root this negative 6, we're going to get something odd that happens here. So when I go to my calculator, I take square root of negative 6. It yells at me. It says this is a non-real answer. And what it ends up bringing up is something we're going to actually talk about in a future lesson is what's called a complex number or an imaginary number. Okay, so basically what this tells us as of now, because we don't get a real number, is that there aren't any x-intercepts. Okay, this particular graph does not cross the x-axis, and that's because of us taking a square root of a negative and getting non-real numbers for the x-intercepts. So our x-intercepts, there are none. Okay, and what's going to happen when you graph this, your vertex is left 2 and up 3, and then it's going to end up opening up. And since it opens up and that vertex is above the x-axis, it never actually crosses the x-axis there. Okay, so whenever you work it out and you get that non-real answer to show up, that means that we don't graph those points. Those points do not show up anywhere on the actual graph. Okay, so I just wanted to point that out before you all get to that place in the homework and then you're like, wait, what the heck is going on here? I'm going to leave the rest of that problem for you all to work through on your own. And now let's actually back up and talk about our last form that we didn't get to yesterday in graphing the standard form. So again, if you weren't here yesterday, or even if you were, remember that everything that we need to do to graph these functions is on this first page. Okay, so this is our standard form. A, B, and C are constants, and this is the form that we dealt with to factor, right? We started in the standard form and we factored to get into its factored form. So starting with, let's come back to the vertex, but if I want to find the x-intercepts, I let y equal 0, so f of x is 0, and then we solve for x, which means we need to factor. Okay, we will have to factor to get the x-intercepts when it's in standard form. To find the y-intercept, we let x equal 0, and then we'll solve for y. That's been the same for all of them. Now, the big difference here is the x-coordinate of the vertex, the way that we find the vertex, it's not as obvious as it is in vertex form or even in the factored form. In standard form, we have to use this quick short formula. X equals negative b over 2a. And let's make a note that we need to know that. Okay, so memorize that. And when I'm talking about b and a, I'm only talking about the numbers in front of the variables. B is the number in front of the x. A is the number in front of the x squared. We don't use the x's with these, just the numbers. So after we use negative b over 2a, that gives me my x coordinate. Then to find the y coordinate, we take that value and plug it right back into the equation, and that's how we're going to get y. Basically, we did that exact same thing when finding the y coordinate of the vertex in its factored form. Okay, so let's now go ahead and put all this to use and work on graphing this one example in standard form. So this form is standard. And let's start with the x-intercepts. And to find x-intercepts, we let y equal 0. So this is 0 equals x squared minus x minus 6. When I have a whole equation equal to 0, this should tell me I need to factor and then use that zero product property to find each x-intercept here. So one thing I'm noticing is that a is 1 here. When a is 1, we have a shortcut for that, and I don't need to use boxes or factor by grouping. But I definitely still need to find two numbers that add to b, where b is negative 1, and multiply to a times c, which is negative 6. Those numbers are negative 3 and positive 2. The 3 does have to be negative, so that way they add to a negative 1. Now, because a is 1, my factors end up being the same or using these same numbers that we found to meet these conditions. So it's 0 equals x minus 3 times x plus 2. Now, if you're like, I don't know how we can make that jump or where that shortcut is coming from, factor it the exact same way you've been factoring all week long before we went on break. Use the box, use the factor by grouping, whatever that might be willing to do that. But again, the shortcut here works because a is 1. After we factor, this is where we use that zero product property and take each factor and set them equal to 0. So x minus 3 equals 0. And x plus 2 equals 0. And I got to add 3 to get x equals 3, and minus 2 to get x equals negative 2. So we have two x-intercepts at 3, 0, and negative 2, 0. All right, then to find the y-intercept, that's always the same, where we just let x be 0, and it actually goes pretty quick here. So we're technically finding f of 0, so 0 squared minus 0 minus 6. Well, 0 squared is 0, minus 0 is 0 that doesn't change it, so it just ends up being negative 6. And a lot of you might make the connection that your y-intercept is that value of c. Okay, when it's in the standard form, that c value will always end up being your y-intercept, because of what happens when we plug in 0 for the x's. So the y-intercept is at 0, negative 6. Okay, so now for the vertex. And the vertex, a lot of your vertexes and points on all these graphs, I didn't make them really nice numbers. They're going to be decimals. Okay, so don't shy away from those decimals and or fractions. So we need to use the x equals negative b over 2a. And again, b is the number in front of the x. So that b value is negative 1. Negative b means to multiply that value by negative 1. So negative 1 times negative 1 makes that to be a positive 1. Okay, so negative b is positive 1. Then a is the number in front of the x squared, and if there's no number there, that's just a 1. So it's 2 times 1, which is 2, making our x coordinate 1/2. So I'm going to leave that as 1/2. It might be helpful to convert it to a decimal, just because when it's in its decimal form, we know exactly where to plot it, right? 0.5, I need to put in between 0 and 1. When it's 1/2, that one's not too bad, but fractions, we usually have to do the division anyways to figure out exactly where to place it on our graph. All right, so now that I have x, for me to find y, I need to take this value of x and sub it into the equation. So that's telling us to find f of 1/2. So that's 1/2 squared minus 1/2 minus 6. and I'm going to let the calculator do all that work for me. Okay, we don't need to go and do all the fraction work by hand. Okay, we are going to get plenty of work with fractions second semester, but for now, we can just let the calculators do the work, which, if you didn't hear my excitement yesterday, the calculators did get returned, so I brought them back. Right after I brought them back, one died on me, so one's down for good. The pink one doesn't hold a charge anymore. So I only have 8 calculators over there. Anyways, calculators are in here if you need them. I'm going to, again, plug everything in the way that I see it. Parentheses around these value, the x value is so important, especially now that it's a fraction. Okay, so 1/2 squared minus 1/2, and then minus 6 gives me negative 6.25. Now, I would leave it as the fraction, but if you do want to convert it and make it consistent and get it into a fraction, if you press this math button, and I have showed us this before, but if you press math, the first option is frac, meaning turn that decimal into a fraction. So I press enter. It says answer, referring to that previous answer I got. Convert to a fraction. Enter one more time is negative 25/4. So the y coordinate is negative 6.25 as a decimal, or negative 25/4 as a fraction. Okay, those are the exact same point. One in fraction form, one in decimal form. All right, so now we just need to plot all of these points. X-intercept at 3, 0, negative 2, 0. Y-intercept at 0, negative 6, so 3, 4, 5, 6. And then the vertex at 0.5, so just barely to the right of the y-axis. Negative 6.25, so just barely below that y-intercept. And plot these points to get our rough sketch. Okay. So questions here before we move on and do one word problem. And with the word problem, first off, I don't like this problem. It's not written all that well. I should have double checked. I'll explain why here in just a second. But the reason that I mixed in these word problems with this activity, it says it on the front, where on the front, one of the very first things that I had to take note of here is that when we're graphing quadratics and finding these 4 key points, these 4 points are typically the solutions to application problems, meaning we're either looking for the vertex or an x-intercept or a y-intercept. Okay, so with quadratic word problems, I know there's plenty of you in here that are like, Mr. Younger, word problems, I can't do them. They take practice, and in my opinion, these word problems are much easier than what we did previously because we don't need to build the equation. The equation is there for us. Instead, what we need to figure out is what part of the graph are we specifically looking for. Now, there's one key thing that I want us to add into the front here. So go back to the front page of this. And when we talk about vertexes, because quadratic graphs either open up and have a minimum or open down and have a maximum, these are also the vertex points. So whenever you see in a word problem, find the minimum or maximum, it is almost always referring to that vertex point. Okay, so when you see minimum or maximum, you should be thinking vertex. And depending on the form the equation is given to us, we've got to find that vertex from there. Okay, so now let's go back and actually start this application. And I'll tell you the was written. So it says the ball is thrown in the air. The path of the ball is represented by the equation h of t. We need to graph the equation over the interval from 0 to 8 on the grid. Nowhere in there does it tell us what the height is being measured in, either meters or feet. It does say it if we read A, B, and C. In B, it says, how long is the ball above 5 meters? So that tells me that we're measuring the height of this ball in meters. But the other thing that it doesn't specify very well, okay, it's subtle, is what our x-axis is going to represent. When we're talking about modeling the path of a ball, The x-axis could be the horizontal distance of that ball, right? If you think about me throwing a ball, it's going to go up and it's going to go out. So the x-axis could be how far out it goes, or it could be the time. And the problem needs to specify what the x-axis is, and this doesn't do a great job of that. Okay, so problem should have been written a little bit better. It does say time here in part D. So what we're going to do is we're going to let our x-axis be in time, and let's let that be seconds. Okay, again, the problem should specify before we even start, but it doesn't do so. And then the y-axis is our height of the ball in meters. Okay, and in this case, we can actually let our scalings all be by 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And instead of graphing this right away, we're going to jump into the questions, because the questions are going to have us finding most of those key points anyways, and we need those key points to graph our function. Okay, so the first thing, it says, what is the maximum height of the ball? Well, when I see that word maximum, that's telling me to find the vertex. And I'm like, okay, with that vertex, do I care about the x coordinate or y coordinate? Well, the height is our y-axis. So we are looking for the y coordinate of the vertex. Using the equation, I now need to think about how do I find the vertex of this particular equation. This is in standard form, so we need to use negative b over 2a. Okay, so negative b is negative 6. A is negative 1, so 2 times negative 1 is our denominator. So negative 6 divided by negative 2, which is 3. Then we have x to find y. We take that 3 and plug it right back in. So now I'm finding h of 3, which is negative 3 squared plus 6 times 3. So 3 squared is 9, but then it does get multiplied by that negative 1 in front, so that negative does not go away yet. Okay, the whole term is negative after we square it. Then 6 times 3 is 18, and negative 9 plus 18 is 9. So h of 3 equals 9, meaning our vertex is at 3, 9. We can plot that. And we can answer the question where the maximum height of the ball is this y coordinate of 9 meters. Part B says, how long is the ball above 5 meters? We're going to come back and answer that question after we have our graph. With the graph, we can solve for that. I don't want to solve for that quite yet. I want to focus more on the graphing piece. So let's skip B for now. C, when does the ball hit the ground? Well, think about if I just made a quick sketch of what it looks like to throw a ball in the air, that can help me figure out what the key point is for where the ball hits the ground. Well, if I'm throwing a ball, right, it's not going to start on the ground, right? When we throw a ball, it's not like we're starting it from the ground and then launching it straight up, right? It's actually starting from about where my shoulder is. Okay, so the ball is starting from a height a little bit above the ground, depending on how tall we are. It reaches a maximum point and then starts to head back towards the ground. And I'm like, oh, it hits the ground at that point there. Well, what's the name of that point in terms of graphs? The x-intercept. So where the ball hits the ground has us finding the x-intercepts. So I'm like, okay, I need to find the x-intercepts. This is in a standard form, so I need to factor this to find those x-intercepts. Also, when we find x-intercepts, we let y equal 0, so it's 0 equals negative t squared plus 6t. I'm looking at this, I'm like, okay, there's 2 terms. Factoring with 2 terms, I know there's a bunch of ways of how that can happen. Before I even think about those ways, I know that I should always first look for a greatest common factor. And I'm seeing one, right? Both of these terms have the variable t. And getting that variable as a greatest common factor is the most important part of greatest common factors. So I'm going to take out the t, and when I divide all those terms by t, I get negative t plus 6 left over. And that's done, right? That is factored. And that's why the variable part of a greatest common factor is so important. When it's just a variable, I don't need to use boxes. I don't need to use factor by grouping. I don't need to find numbers that add to b and multiply to a times c. And now I can take each factored term and set it equal to 0 to find the x-intercepts. So t equals 0, then negative t plus 6 equals 0. T equals 0, there's nothing left for us to solve. That is done. That's one of my x-intercepts. Negative t plus 6, I need to subtract 6 and then divide by negative 1 and get that t is a positive 6. That is our other x-intercept. So our x-intercepts are at 0 and 6. And this is good enough for us to go ahead and make the graph from here. Okay, we'll do our best to connect these dots. It does not need to be perfect. Give it that U shape. Okay, and now that's going to allow us to answer the rest of these questions. Okay, so back to C, answering that question, when does the ball hit the ground? Well, it hits the ground at this particular point there, which happens after 6 seconds. So in 6 seconds, it hits the ground. Right, part B says, how long is the ball above 5 meters? Well, for me to figure that out, I'm going to figure out when the ball first gets to 5 meters, which is right here, kind of at 1 second. It might be a little bit less. It's really an estimate at this point. Again, we could solve this. We're going to skip the solving part for now, and I'm just going to kind of estimate it. And I go, okay, it gets to 5 meters on its way up, and then it stays above that until it starts to head back down, and then eventually it gets back to 5 meters again, and then it's below that the rest of the way. So the time that it is above 5 meters is this horizontal distance in between those 2 points. And so that is, looks like it's 1, 2, 3, 4. So it is about 4 seconds. Again, we can just use the graph to estimate that. Eventually, we will actually extend this and solve for that particular value. We don't need to do that here, though. All right, and then part D, kind of same idea. At what time does the ball reach 8 meters? Well, I'm going to go to 8 meters, and I see that it gets there in 2 places. Okay, it appears to get there after 2 seconds. But then it also gets to 8 meters again on its way down at 4 seconds. So after 2 seconds, and again at 4 seconds. Okay, I think technically when does the ball reach 8 meters, it's just looking for the 2 seconds there. But I do want to point out that there's actually 2 places that it gets to that 8 meters, on its way up and on its way down. All right,